Hi, my name is my matric number is 244698.
And my name is Amir binti Azham, and my matrix number is 225547. And we are from Group 3, Discrete Structure.
And we're going to present to you our project mini, which is under graph theory, which is isomorphism. We're going to present to you.
So, what is isomorphism? Isomorphism is a graph that can be described as a single graph that can have more than one form. Two graphs that are not only similar but are identical are known as isomorphic. In order for two graphs to be isomorphic, they must have the same number of edges, the same number of vertices, and the same number degree of each vertices. Okay, let's move on. In general, the term isomorphism is widely used to refer the concept of sameness. Requirements for two objects considered as isomorphic is when, if any object is same as itself, it is in reflexive properties. For second requirement, if A is equal to B, then B is equal to A, that is symmetry property. And for the last requirement, if A is equal to B and B is equal to C, then A is equal to C, which is known as transitive properties. A relation that has these three requirements are called equivalence relation. Let's look at a real-life example that can demonstrate isomorphism more clearly. A good example is playing chess. As two players are playing chess and they decide to leave halfway through the game, the players will take note of where all the pieces are and all the information about the game that they have played. When they decide to continue the game on a board that is similar and identical to a chess set, for example, we have here a Super Mario themed chess. They can easily do that by just using the numbers that I jotted down earlier. They can continue the game by just plugging in the chess pieces of the game into the isomorphism that can preserve the structure of the game. If they were to continue the game on a different game board, such as a Monopoly board game, do you think it would be possible?
No.
Yes, it won't be possible because the two boards they do not have the same structure. They are not identical. They are not isomorphic. And it won't be possible to continue chess on a Monopoly.
Now let's move on to isomorphism graph. Isomorphism is the graph is represented in more than one form. So like this one, we have this square, we have this square and also this slash. And then look at the colored point list, or we call it vertices. This one we call it vertices. And then this is the edge, the line we call it edge. This one, 2. We call it the degree of vertices. This is like 3 degree of vertices. Okay. And also, we can see there's a very different kind of shape. A very similar property, even its shape is different. For main conditions for the graph to be isomorphic is equal number of vertices, equal number of edges, equal amount of degree sequence, and also if the first graph forming a cycle of length of A with the help of vertices B1, B2, B3 until Dk. Then another graph must also form the same cycle B1, B2, B3 until Dk. But we couldn't say that if we satisfy this four main condition, we couldn't say it's isomorphism yet because it is not necessary that the above defined condition will be sufficient to show that the given graph are isomorphic because we have this condition, which we call it sufficient condition, or I usually call it special condition. So this is when we need to draw the complement graph of both the graph. If the complement graph of both the graph are isomorphism, then this graph will surely be an isomorphism. For example, this is the original of the graph. Then we're gonna draw a complementary of graph. This is when we need to draw a line that never yet drawn here. For example, for this one, we have this 4 line and so this line. So which line that we didn't have yet is this line. And then we can say that this is the complementary of the line. If you see carefully, which this all line was connected with the same point, right? Look at the color. Green to dark blue. Green to dark blue. Green to dark blue. Green to dark blue. So we can say that it's isomorphic. Alright, let's move on to the example 1. So they have these 3 graphs, G1, G2, and G3. So which of these graphs are isomorphic to each other? We need to look at 4 conditions that we just learned now. Check for the condition 1 first, which is the number of vertices. G1 have the number of vertices of 4. Okay, let's go to the G2. How much the number of vertices have in the G2?
4 number of vertices.
Yeah, very well. And for the last graph,
1, 2, 3, 4.
4, that's correct. So like we can say that all these graphs equal amount of vertices. In conclusion is we can say that these 3 graphs, which is G1, G2, and G3 already satisfy the condition 1. Okay, let's consider condition 2, which is the number of edges. We're going to look at the graph 1 first, which is G1. Have 1, 2, 3, 4, 5. And how about this one? 1, 2, 3, 4, 5. This is also have 5 edges. How about this one?
let's see. Here is 1 edge, 2, 3, and this one is 4. So the number of edges is 4, right?
Yes. And then this is equal, but this is not. For the G1 and G2, G1, G2 already satisfy condition 2. But because of the G3 have number of edges of 4, so G1 and G2 already satisfy the condition 1. But because we don't have the equal amount of the edges, so we couldn't say that the G3 is the isomorphic. Since G3 already provided the condition 2, G3 not isomorphic. So in the end, we need to eliminate G3 for the condition 3, because for the condition 3, we need to see for the G1 and G2 if these two graphs is isomorphic or not. So let's go to the condition 3, which is the degree of sequence. So what is the degree of sequence? So if there's a vertex, there is a vertex, and then vertex, and then we have the edge. The number of degree is when a vertex, the number of lines that came out from a particular vertex. For example, this one vertex, we have one line that came out from it, 2 lines and 3 lines. I mean edges. So we can say that this is three number of degrees for this vertex. And then for this one, only 1. And then we can say that it's 1 degree of vertex. That's it. So let's move on to the question. We have graph 1, G1, which is this one. We have for this vertex is 1, 2. This vertex is 1, 2, 3. This vertex is 2. And this vertex is 3. Right?
Yeah.
So for the G2, we have 1, 2. This one we have 1, 2. This one we have 1, 2, 3. This one we have 1, 2, 3. So we can say that for this one first, I'm gonna go through this one first. The number of degree sequence. Okay, for this one, number of degree sequence is 3, 3, 2, 2. So if you observe it very carefully, is there any differences or is it same?
They are the same.
Yes, right. So we can say that G1 and G2 satisfy, is equal lah. So satisfy the condition D. Let's move on to the fourth condition, which is the cycle of length. The cycle of length is when, for example, we have this D1 right, D1, and then we can say that the cycle is from here to here to here. Cycle is when one vertices, the vertices with a length, with a edge, and we need to stop with the same vertices like this. This is we call the cycle. Okay. So if you just left it hanging, it's not a cycle.
Because it's not connected.
Yes, it's not connected to the initial point that we started. Yeah, we need to start with that vertex, and we need to stop with that vertex. Right. That's why for this cycle of line, we form a cycle basically within this graph. Okay. The cycle of length for this question is this one, and this one. So we have 1 vertex, 2 vertex, and 3 vertex. So we can say that the length cycle of length of 3. The 3 refer to the vertex itself. We need to know the number of degree of each of the vertex that we put. This is 3, this is 2, this is 3. 3, 3, 2. Okay, for this one, 1, 2, 3. Also the same. So we have this one, 1, 2, 3. This one, 1, 2, 3. And this one is 2. So you can say that the cycle of length of 3 with the help of 3, 3, 2. They are the same, right? That's why you can say that G1 and G2 satisfy condition 4. Okay. But we didn't end yet. So for the G1 and G2, we already have 4 conditions satisfied successfully. But we need to look at one special condition, which is sufficient condition. We need to draw the complementary graph to make sure that it's isomorphic or not. So the original graph is like this. Right. We need to complement the graph with the missing line that didn't have in the original graph. That's why we could say that it's shown that the complementary graph of G1 and G2, therefore graph G1 and G2 is isomorphism. So So my part already done. How about you doing your part with example 2?
Example 2, based on the conditions that we have here. So in order to really know if they are isomorphic or not, let's check the 4 conditions. So first I will draw the first graph. This is graph 2. So condition 1, we will look at the number of vertex. We have 1, 2, 3, 4, 5, 6, 7. So we have 7 vertices for graph 1. And now we will look at graph 2. So here we have 1, 2, 3, 4, 5, 6, 7. Graph 2 also has 7 vertices. So from what we can see here, they are both equal, right?
Right.
They are both equal. So therefore, graph 1 and graph 2 satisfies condition 1. And because of that, we will move on to the second condition. Okay, now we will check the number of edges. This has 1 edge, 2, 3, 4, 5, 6, 7, 8. This one, graph 1 has 8 edges. Moving on to graph 2, we have 1, 2, 3, 4, 5, 6, 7, and 3 is 8. Graph 2 has 8 edges. So we can see that they are both equal. Therefore, graph 1 and graph 2 satisfies second condition. Okay, now we will move on to the third condition and we will check the degree of sequence in both the graphs. To look at the vertices, right? And we have to look at the lines that come out of the vertices. That is the number of degree. So from here, starting from here, we can see this has 2, and this one has 4. This one has 4. Here has 1. This one has 2, and this one also has 2. Like you said earlier, in order for us to see better, we will arrange them from the biggest number to the lowest. So 4, 4, 2, 3, 2, 1, and 1. Now we will look at the second graph. The number of vertices is 2, 3, here is 2, here is 2, 4, here is 1, and here is also 1. And when we arrange it from highest to lowest number, we will get 4, 3, 3, 2, 1, and 1. So from here we can see that they are not the same, right?
Yes. They have very significant differences.
Therefore, we can say that graph 1 and graph 2 do not satisfy the third condition. Graph 1 and graph 2 is not isomorphic.
So how about the condition 4?
We can move on to condition 4. Because since it already violates condition 3, it cannot be isomorphic. In order for it to be isomorphic, it must fulfill all the 4 conditions.
Oh, I see. Now, we already see 2 examples where those shapes were very simple and so like we could easily identify it by the first glance. How about we move to a slightly difficult shape like this one? By using what we have learned just now, how do we solve this problem? Do you know how to solve the problem?
I don't know. Hey you, do you know how to solve this problem?
If you know, take out your notes and pen. We need to do this together.
Yeah.
Let's go. Condition 1 is about what?
Condition 1 is to check the number of vertices.
Yeah, vertices. For the graph 1, for the first one is 1, 2, 3, 4, 5, 6. So for the number of vertices, we have
6 vertices.
6 vertices. And then how about this one? We have 1, 2, 3, 4, 5, 6. We have number of vertices of 6. So it's equal. So we can say that G1 and G2 satisfy condition 1. Okay, let's move on. So we go to the condition 2, which is related with ages. So for the graph 1, we need to count together. 1, 2, 3, 4, 5, 6, 7, 8, 9. It already has 9 number of ages. How about this one? How about this one? We need to count together. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 6 also have 9 edges. So since it's equal, we can say that G1 and G2 satisfy the second condition, condition 2.
For condition 3, we will check the degree of sequence. Now that I have drawn them, let's count the number of degree of sequence. So from here, you can see 3, 3, 3, 3, 3, and 3. So that is the degree of sequence for graph 1. And next for graph 2, let's start from here. There is 3, 3, 3, 3, and 3. And so, from what we can see, they both have the same degree of sequence.
We have 6 sequence, right?
Yeah, they are both 3, 3, 3, 3, 3, 3. And here also 3, 3, 3, 3, 3, 3. So it satisfies condition 3. And then we can move on to condition 4. Condition 4, which is we count the cycle length. Let me just draw the graphs. Okay, let's count the cycle length. From here we can see the length is, we can see the cycle. Starting from here, and then we go here, 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 and then come back to here. That is one cycle, right? And the cycle length you can see is based on the edges of each vertices that connect the cycle. The cycle of length here is 3, and here is 3, here is also 3, and here is also 3. So that is the cycle length for graph 1. Now we will look at graph 2. We can see the cycle will start from here, comes to here, comes to here, here, and comes back here. So now we will count the length, the cycle length, which is 3, 3, here is 3, and here is also 3. So from what we can see, they both have the same cycle length. Therefore, graph 1 and graph 2 satisfies condition 4.
So I have a question. How about we start from the different vertices?
We can also start from different vertices. For example, we can start from here, right? And then we can go here, here. We can just go until we can form one cycle. And if we count here, so also 3, 3, 3, 3. It also has the same. It also has the same cycle length. So it doesn't matter where you want to start. The same goes with this one.
Right, where we starting here?
We can start from here, and then we can go from here, and then we can go from here, here, and then we can come back here.
Oh.
And if we check, it still has the same cycle length. So it doesn't matter where you want to start.
Oh, I see.
Yeah.
Since most of the graph already satisfy the third condition, we still have another condition, sufficient condition. Is where we need to do the complementary graph. Okay, we already have this already the graph. And how about the complementary? You need to draw the missing line that didn't have drawn yet in the graph. Okay, this is the complementary of the graph. We look into the fourth condition that we have learned. So we have, we need to clean up the original one. We just left this one. Okay. So we have these 6 vertices. This is also 6 vertices. And then for the edges, how much edges do you think this? 1, 2, 3, 4, 5, 6. Well, have 6. How about this? 1, 2, 3, 4, 5, 6. We have also 6 edges. So how about the degree? The degree sequence. This one we have these 2. It's also 2. These 2, these 2, these 2, and this 2. So I have 2, 3, 2, 2, 2. For 6 times, we can have 6 vertices. Same goes to this one. With this one. 2, 2, 2, 2, 2. Right. 2, 2, 2, 2, 2, 2. Okay, the last condition is cycle of length. Cycle of length is when I need to put the highlight. 1, 2, 3. This is also 1, 2, 3. So what is it? We can say that the cycle of length of 3 with the help of vertices 2, 2, 2. And then for this one, you can say that the cycle of length, is 3. Is also 3 with the help of vertices 2, 2, and 2. So with all the sufficient conditions have been satisfied, so we can say that Gy and G2 was proven the isomorphism. So let's move on to the conclusion, shall we?
So in conclusion, graph isomorphism is a fundamental concept in our daily life, especially in computer science, as it deals with the structural similarity between two graphs. It plays a crucial role in various computational tasks and has far-reaching implications in areas such as network analysis, database management, image recognition, and many more. So I think this is the end of our discussion on isomorphism.
Thank you very much for watching. Bye.
Bye.